The goal of this experiment was to gather various observations about a charged piece of tape's behavior and to estimate its charge. This experiment involves physical principles of Coulomb's law, how charged objects interact with each other and with neutral objects, and how the signs of charges determine the direction of the resultant force. To gather information about the behavior and interactions of charged tape, the tape, which begins largely as neutral, was charged. This was done by sticking two pieces, each measuring about 8 inches, together, then quickly ripping them apart. The charged tape was then held to various objects for observations. Among these were a hand, which the tape was attracted to, another piece of tape, which repelled each other, a pin, which was given a negative charge by rubbing it on hair, which attracted the tape, and a table, which also attracted the tape. To estimate the charge of the tape, it was attached to two upright books that were placed at a distance slightly lesser than the length of the tape to allow it to bend slightly. A second piece of charged tape, which was created the same way as the first, was placed under the fixed tape and moved closer to the fixed tape until the fixed tape began to float. This distance, which represents the magnitude of the r vector, was recorded as 0.019 meters. The electrical force of the bottom piece on the top piece is equal to the force of gravity on the top piece. This is known because the tape is at rest, indicating the downward acting force of gravity is balanced out by the upward acting force of the tape. To find the force of gravity on the top piece, the mass of the tape was estimated. This value was found to be 0.00016 kilograms, and when multiplied by the acceleration due to gravity, it yields the force of gravity, which was found to be 0.0016 newtons. Knowing this force is equivalent to the electrical force, the charge of the tape could be found using Coulomb's law, an equation that models the force experienced by a charge placed in an electric field. In this experiment, Q1 and Q2 represent the charges of the pieces of tape, and the magnitude of the r vector represents the distance between the two pieces. Assuming that both tape pieces have equal and evenly distributed charge allows Q1 times Q2 to be replaced with Q1 times Q1, or Q1 squared. Also, because the forces are acting purely vertically, the unit vector of r can be ignored as long as it is kept in mind that the resultant force is acting upwards. Using this simplified form of Coulomb's law, and recalling that the electrical force must equal the gravitational force and the recorded magnitude of r, we can solve this equation for the charge of the tape pieces and get a value of 7.95 times 10 to the negative 9 coulombs. To determine the sign of the charge, the calculated charge was divided by the charge of a single particle. This value was recorded to be 4.97 times 10 to the 10 power electrons, and represents either a surplus or deficit of electrons. To find which, this number was compared to an estimated total number of atoms on the piece of tape. This number was found by dividing the area of the tape by the area of a single atom, and gave a result of 2.57 times 10 to the 17 atoms. The ratio of charged particles, electrons, to atoms was 1.93 times 10 to the negative 7, indicating that the tape had lost electrons and was positively charged. This conclusion is in line with the observations made with the various objects, as it was attracted to the negatively charged and neutral objects and repelled by the positively charged objects. If protons and electrons switched charge signs, the observations for the tape being attracted to the hand, the two tapes repelling each other, the tape being attracted to the neutral table, and the pin attracting the tape would all be the same, as these observations are the result of whether the signs of the charges of the objects involved are alike or opposite. Since we are assuming that both protons and electrons switch signs, there is no effect on these observations. When making and handling the charged tape, it was important to touch it minimally because the charged tapes have a tendency to balance out their charge by transferring their excess positive or negative charge onto other, less charged objects that they come in contact with. The magnitude of the charge on a single piece of tape was calculated by my computational model to be 7.95 times 10 to the negative 9 coulombs.